differentiation, and I had done a couple of examples, right? I thought we did, yeah, exponential and logarithmic differentiation. Were there any questions? Anything you wanted me to discuss on that? Problem number 33.
Not 33.
28 out of 3.3? E to the u, that one? Okay. All right, where are we at here? All right, so you're given an equation which is implying that y is a function of the variable u, e to the u minus e to the negative u over e to the u plus e to the negative u. And you're asked to find the derivative, right? Differentiate the function. Well, the fact that you see a bunch of e's in here, right? You know that natural log together with e, they go away. So maybe there's something we can do with that. What do y'all think? You want to start with that? Let's see how bad this gets. So logarithmic differentiation, what you have to do first is what? Take the natural log on both sides. So natural log of y should equal the natural log of a quotient, right? And then I can use the property of logs that if I have division inside of a log, I can split that into two logs and make it two logs with subtraction. So the left side is natural log y. I'm not going to touch that. Then natural log of e to the u minus e to the negative u, then minus natural log e to the u plus e to the negative u. Right? Now, can I split these two up? Like, because I have this subtraction in two terms, can I split that into two logs? No. That would only work if it was multiplication in there, wouldn't it? Yes? So we would have no choice if we continue down this road to just differentiate at this point, right?
You couldn't take the u's out, like put them in front of the ln?
Good point. What we would have to use that property is this. Remember, the property says if you have natural log of something, it doesn't matter what it is, to a power, that the power can come out. But the power has to be acting on the entire argument of the function. So the u here would have to be acting on everything there. And here it's separated. You have a u acting on the e, and then you have a negative u acting on this. So unless you can somehow make this, all of this to the u power, you can't pull the u out. Agreed? Could we make that all to the u power? E to the u minus e to the negative u. Is there a way that I could write that as something to the u? Think about what it means when you raise something. If we have two terms in here, right, let's say x and y, that don't you have to expand it all out and it gets real messy? Like, you can't just put the u on each one, can you? Algebra would be a lot easier if that were the case. But so I don't see an easy way that we could do that. So maybe just differentiate now, see what happens. Yeah. Let's just see. So the derivative left side is going to be 1 over y prime. The derivative of the right side. So what is the derivative of natural log of anything? 1 over that anything, right? So 1 over e to the u minus e to the negative u. Then chain rule, derivative of what's inside. So what's the derivative of e to the u? Because these are two different terms, I'm doing derivative, right? E to the u. And then natural log of e, which is 1, right? What's the derivative? Oh, I should be putting it, I've been putting it on the outside. It doesn't matter. I'm going to slide it over in the next step. So 1 over this times the derivative of what was in there, which we're saying was e to the u, minus, now be careful on this one, the derivative of e to the negative u is e to the negative u, times the derivative of what's up here. What's the derivative of what's up here? What's the derivative of negative u? What's the derivative of negative x with respect to x? Negative 1? So when you take the derivative of what's up here, you have to take derivative of negative u, which is negative 1. But it was already minus, right? So it's actually going to become plus e to the negative u. Maybe I need to show that. The derivative of e to the negative u is itself times derivative of what's up here, which is negative 1. But there was already a negative out here, so that's why it's switched it to a plus. And then minus. Derivative of natural log of something is 1 over it. And then times the derivative of what's in here. So what's the derivative of what's in there? I'm out of room. E to the u, then minus e to the negative u. Y'all okay on this so far? All right, let me try and write down what we've got here. I've got 1 over y prime equals e to the u plus e to the negative u over e to the u minus e to the negative u. That's putting these two together in a fraction. And then this one minus the top e to the u minus e to the negative u over e to the u plus e to the negative u. Is that all right? What the heck do you want to do with that? I'm sure that's not the answer in the back of the book.
Well, you could slide over, like you said before.
Do what?
You could slide over the product, put it on top of the numerator.
Which one? This?
Yes, well, to each one.
Yeah.
Fraction.
Well, that's what I did there, right?
Oh, sorry, yes.
Right? So that's what you were saying, right? Just put that on top. You could do a common denominator. You could do a common denominator. Right now, they're not the same, right? It would be real nice if these were both pluses, right? But they're not. So I would have to introduce what would I have to introduce on the top and bottom here and over here? So e to the u plus e to the negative u on top and bottom here. E to the u minus e to the negative u top and bottom here. Do y'all want to do that? Yes? Okay. Well, I don't really see many other options. I'm thinking something in the beginning maybe we might have been able to do, but I'll get back to that maybe after I do this. I'm doing what you all kind of directed me to do here, so I'll go a little slow. E to the u plus e to the negative u is what I'm introducing on the top and bottom here. E to the u plus e to the negative u. I'm going to be multiplying that times that first fraction, e to the u plus e to the negative u over e to the u minus e to the negative u. All right, that's just to get a common under here. Then minus, here's the other fraction. And what am I multiplying this one by? E to the u minus e to the negative u over e to the u minus e to the negative u. That should give me a common denominator, shouldn't it? Okay, what do I get when I multiply these two together up on top? We get, it's that squared, isn't it? But if I actually FOILed it out, did all the multiplication, what's e to the u times e to the u? E to the 2u. Now, let's make sure we're all aware of that. That caught my Cal 2 students on their test last week. E to the u times e to the u is e to the u squared, isn't it? Yeah. And then when you have something to a power, you multiply these two. So that's 2u. Agreed? Okay, so that's this to this is e to the u, e to the 2u. How about this times this? What's e to the u times e to the negative u? So what do you do to exponents? Like here I could have said, what, u plus u is 2u? I just add these exponents because they have the same base. Here, if they have the same base, I add the exponents, what do I get? E to the 0, don't I? What's e to the 0? 1. So that multiplication from, we did that one, sorry. From here to here is 1, isn't it? Plus 1. What's this one going to be? Plus 1 again. And then what's this times this? E to the negative 2u. Y'all okay with that? Now, I'm going to do the same thing over here. These two together, because I know it's all over the same common denominator, isn't it? I'm going to do those two together. What would I get if I did e to the u times e to the u? E to the 2u, right? But then I'm going to subtract it. So minus e to the 2u. What do I get when I multiply e to the u times e to the times negative e to the negative u? These two. That'll be negative 1, won't it? Because this times this is 1, but then it's negative. So negative 1, but then I'm doing what? Subtracting, so it's plus 1. How about here to here? It'll be minus 1 here, right? But then minus, so plus 1 again. And then what about the last multiplication? Minus and minus is plus, right? But then I'm going to subtract it, so minus e to what power? Negative 2u. That's all over the common denominator, which is what? These two multiplied together? Do you want to do those? Those will probably turn out to be pretty nice. What's e to the u times e to the u? E to the 2u? What about the middle terms? They cancel. And then what about the last one? Minus e to the negative 2u. Now, remember the left side of this is 1 over y prime. And then I think we get some good cancellation here, don't we? This cancels with this. This cancels with this. These numbers add up to be 4. 1 plus 1 plus 1 plus 1. So you get 4 over this denominator. Do you agree? Yeah. So here's where I'm at. I'm at 1 over y prime equals 4 over e to the 2u minus e to the negative 2u. And what would be my next step? Multiply both sides by y. But what was y? It was the original problem, wasn't it? So what was it? I forgot. E to the u minus e to the negative u? Oh. So e to the u minus e to the negative u over e to the u plus e to the negative u. Is that the answer in the back, though? I don't know. That's an even? Okay, that'd probably be okay. You could distribute a 4 through here. You could put this in parentheses next to this. You could even multiply those together if you wanted to. But I think the main gist of how the problem is done is already done now. Everyone understand that this is y?
Yes.
Y on both sides? All right, now if I were to be looking at this problem to start off again, okay, if I were doing this problem, I might do it a little different. Let me see. Let me just take a look at it again. I'll tell you what my instinct would have been on this. I think that's the original problem. I would have rewritten this just to see what happens as e to the u minus 1 over e to the u over e to the u plus 1 over e to the u. Do we agree that those are the same things? Yeah? E to the negative u is the same as 1 over e to the positive u. And then I would have done something like clearing out fractions. I would have multiplied the top and bottom by e to the u. Now let's see why this would work. Like what would happen here? I go here to here and here to here, right? On the bottom one, here to here, here to here. So tell me what y would be equal to. I haven't taken any derivatives, right? Just rewriting the original problem. What would this times this be? E to the 2u. Then what? Minus 1 over. The bottom would be e to the 2u plus 1. E to the 2u plus 1. Now at that point, I wouldn't have any real choice other than to do what I did before. Take the natural log on both sides and then split it into 2, and you'd still have to work through it, but your derivative would be a little cleaner. That's all it would just be a little cleaner as the derivative goes. I can show you real quick. Real quick. So that's what would happen. I take natural log on both sides, and then I split that into the two pieces. Then I take the derivative 1 over y prime equals 1 over e to the 2u minus 1 times 2e to the 2u, and then minus 1 over e to the 2u plus 1 times 2 e to the 2u. That look good to you? Derivative of this is 1 over itself times derivative of this. Derivative of this is itself times derivative of what's up here, which is 2. And then same thing over here, except I'll have, let me see, plus, so that's it. Then you put these two together, you'd have to get a common denominator. So it's still kind of messy, but that derivative was a little bit nicer. So I would argue that really doesn't do too much more for you. Okay, let's start today's stuff. We're going to get into 3.5. And if you looked at the notes that are online for this, it's very simple. It's like half a page. It's just formulas. But I did want to take some time to remind you of these inverse trig functions. So remember the way that trig functions work. I can't go back and completely do this like it was done in pre-cal, but I can at least remind you of what the inverse trig functions did. When you look first of all at a function, all right? If I sketch something here and I call that f, if I asked you, is that a function, what would you do to check to see if something was a function? Vertical line test. Would this pass the vertical line test? Yes. Now, if I asked you, does this function have an inverse, then what would you use to check? The horizontal line test. So you draw lines horizontally, and you can't hit more than once, right? Would this have an inverse? I don't know. It looks like right about here, maybe. Maybe I'll exaggerate this a little bit more. There. Okay, doesn't it, if I draw this horizontal line, doesn't it hit more than one time? And because of that, it's not possible to have an inverse. Does this kind of ring a bell? Function, its inverse. How do functions and inverses behave? Well, we've talked about this with natural log and exponential. When you put two functions together, if they're inverses, they undo each other, right? So if I take a function f, I put it together with its inverse, it's going to spit out whatever I plugged in here. So you plug something into the inverse function, plug that into the original function, they wipe each other out and the x falls out. It works the other direction that this works, right? That's the property of two functions being inverses. But back from college algebra and pre-cal, what we learn is that whenever you have functions and inverses, you have to be real careful with their domains. Because if you have a function f, right, this is going to be a picture. If this is the domain, I'm going to say dom f. You have a function that takes numbers, you plug those numbers into a function, it spits them out. This is called the range of f. I'll put ran f. So this is the inputs, the numbers that go into f. These are the outputs. Agreed? Mm-hmm. Then if f has an inverse, if it does, which not every function does, if it has an inverse, the domain of f and the range of f switch places. So look, what is the domain of f inverse? The domain of f inverse is actually the range of f. And the range of f inverse is the domain of f. So the inputs here turn into outputs, right? Those outputs become the inputs of the inverse. The outputs of the inverse become the inputs of the original. So the roles of domain and range switch places. Does that kind of look like something you may have seen? All right. So when we're talking today about inverse trig functions, we need to have a good idea of how our trig functions from pre-cal worked. When it comes to trig, what we had was something like a function, let's take sine x, right? And we said for sine, the things that you plug in here, these were angles, right? Sine of 30 degrees, sine of pi over 2, sine of pi over 6, right? The inputs to the sine function are angles. The outputs, right, were what? Just numbers, right? But what were these numbers? They couldn't be anything, right? They had to always be between negative 1 and 1, right? For the sine function, negative 1 and 1. There's no angle that you can plug into sine to get something bigger than 1 out or smaller than negative. Well, bigger but negative, right? Bigger, negative. What do we mean by big and small when it comes to numbers? This is off subject, but when I say, when you look at a number line, here's 0, I think everyone understands what we mean by big number, right? Everyone always thinks like, this is a big number. Something way out there? Then what's a small number? Close to 0 or just further that way? You see? So there's some kind of gray area. So you have to be pretty specific when you talk about small numbers. Most time when we say a small number, we mean something very close to 0. But we're told that when you put numbers on a number line, the bigger number's to the right, the smaller is to the left, right? So you could theoretically say that negative 1 is smaller than 0. So why do we say this is small? Do you understand the kind of gray area here? So when you want to talk about a number way out there, sometimes you can say a very large negative number. All right? It looks a very, very large negative number, as opposed to a very, very small number, which would be close to 0. All right, off topic, sorry. All right, so back here. We know that the angles get plugged into trig functions, numbers come out. In the case of sine, those numbers have to be between negative 1 and 1. When we go and we try and define an inverse function that takes it back, we run into a problem. Because when you graph sine, it looks like this. And even though it passes the vertical line test, it fails the horizontal line test. So it's impossible for us to define an inverse function unless we do what? Anyone remember what we did? We restricted the domain. So what we did is we came here to the sine function and we said, look, imagine it goes backwards like this, right? And we said, let's cut the sine function off right here at pi over 2 and right here negative pi over 2. And we say just between here and here, if we erase everything else, then between there and there, the sine function achieves every value in its range, doesn't it? Negative 1 to 1 is achieved in there. And cut it this way, it passes both vertical and horizontal line test. So that's why there is a restriction on the domain of sine when we want to talk about the inverse. Make sense? If I don't restrict it, then these angles can come from anywhere, right? 0, 30 degrees, 1,476 degrees, right? You can plug all those into sine. But if we want to be able to come backwards, you have to restrict this. And that restriction has to be between negative pi over 2 and pi over 2. This is pre-cal, all right? Does that look familiar to you? A little bit? The inverse function that comes back, if we do the proper restriction here, the inverse function, the way we write it, is sine with the little negative 1 up there. Or there was another one. What was it? Arc sine x. Those are the same notations. They represent the same thing. So what's the domain of arc sine? What's the domain of the arc sine function?
Negative 1 to the sine function.
It's the range of sine function. So negative 1 to 1? So you would say that the arc sine takes numbers in and spits out what? angles, as opposed to the sine function, which takes angles and spits out numbers. Remember that. Inverse trig functions always spit out angles, right? They always spit out angles. All right, so you go through in pre-cal and you do the same thing for cosine and for tangent, and you come up with these different restrictions. Anyone remember the restriction for cosine? I'll do it in red. I don't want to write the whole picture again. If this was cosine, anyone remember what the restrictions are? This is still negative 1, 1 here, but going backwards it's not. We cut it in a different place. 0 to pi. And that comes from this picture. Cosine looks like this. And so we cut it right here. Like that, and we cut this off. And see, in that little interval, it attains every value in its range. And so that's why the restriction's a little different. What about tangent? Do I have another color? Oh, I do have another color. See if any of these work. Ooh, my lucky day. For tangent, anyone remember the? Yeah, the tangent, anything can come out of tangent. But when you go back this way, right, arctangent, it's the same as, well, it's a little different. You can't actually have, it can't actually be negative pi over 2 and pi over 2. And I'll draw that picture up here just so we have it. All of these should be on your cheat sheets. Anyone have your cheat sheets close by? I'll graph the tangent function. That's what tangent looks like. So you can see the domain restriction. See, and it repeats itself. Remember that? It just keeps on doing that, both sides. So what we do is we just look between negative pi over 2 and pi over 2. It passes the vertical line test in here, passes the horizontal line test in here. So our domain is negative pi over 2 to pi over 2, but we can't include negative pi over 2 because it's undefined there. And we can't include pi over 2. So the domain and range switch places. We good? That's inverse trig functions pre-cal in 5 minutes. Done. All right? Now, you need to be very familiar with the way that, especially tangent, this whole relationship here and what's happening at pi over 2, negative pi over 2. That'll help you out in Cal 2 for sure. But what we're interested in now today is that if these trig functions exist, if we have 6 trig functions from pre-cal, sine x, cosine x, tangent x, let's go cosecant x, secant x, cotangent x, right? Those are our 6 trig functions from Cal 1, from pre-cal, geez. I can also come up with a table here with all their derivatives, right? So here's the function, here's the derivative. So derivative of sine, we already saw was cosine. Derivative of cosine was negative sine. Derivative of tangent was secant squared. Derivative of cosecant, negative cosecant x cotangent x. Close. Derivative of secant, secant x tangent x. And derivative of cotangent is negative cosecant squared x. Those are all on your formula sheet. So we knew this walking in today. 6 trig functions from pre-cal, the 6 derivatives of those 6 trig functions. What I'm doing today is I'm reminding you that in pre-cal there were also 6 inverse trig functions that allowed you to undo these 6, right? And guess what? Each of those 6 inverse trig functions has a derivative. And so that's what we want to look at. So we're going to have a total of 12 trig functions, 6 of them being the standard ones, 6 of them being the inverses, and a total of 12 derivatives, 6 of them being these and the other 6 that we're about to look at. The whole domain thing was just to remind you that as soon as you start throwing inverse trig functions into the game here, you always have to pay attention to domains. It's always something critical to pay attention to. All right, let's start out with if y equals arc sine of x, then what is y prime? So what's the derivative of arc sine? We know derivative of sine of x is cosine x, but what's the derivative of arc sine of x, right? Well, let me show you how we get it, because it's on your formula sheets, isn't it? Oh, and can I look at that? I asked you to pull that out. I just want to look real quick. All the stuff that I was saying, whoa, didn't realize that was there. There you go. All the stuff I was saying about arc sine, I'm trying to see if they have them on here. I thought it had, oh yeah, here we go. It's the bottom of reference page 3. It defines the arc sine, arc cosine, arc tangent, and it talks about the domain restrictions there. So just as a reference, you do have that there on your sheets. Okay. All right, so check out how we do this. I'm going to use the following property. Remember this. Sine of arc sine of x should be equal to what? X. As long as this number right here is in the domain. So that number has to be where then? Between -1 and 1, right? Or it could be -1 or 1. Yes? Because that's a number. This is going to spit out an angle, isn't it? And sine of an angle is going to spit back the number. And so basically it all goes back to where it came from, in essence. So as long as domain restrictions are maintained, that should be an identity we have, or a property we have. And it also works the other way. Okay, that's true, right? All right, using that, I want to come over here and I want to find out what y prime is, right? Okay, so here's what I'm going to do. Anyone have a guess as to what I'm going to do? I can give you a hint. In the logarithmic differentiation, we messed with both sides in order to make this thing happen. I'd like to mess with both sides here, but not log. What do you think I should come in with on both sides here? Sine. Because if I take sine on both sides of this equation, my right side should just turn out to be x, shouldn't it? Yes? So I have sine of y equals x. And what do you think I'm going to do with that? Differentiate with respect to x. I'm going to want to find dy dx. Everything's going to be differentiated, though, with respect to x. All right, so the derivative of sine of y is cosine y times y prime. Very good. So do not forget the chain rule, right? You have to take derivative of sine of something is cosine of it, then derivative of what's inside, derivative of y with respect to x is y prime. And then on the right side, this one's the easy one. Derivative of x is 1 with respect to x, right? What would the derivative of x be with respect to t? Dx dt, but we're saying with respect to x, so that's why it's 1. And so can you solve that for y prime? Absolutely. Y prime is equal to 1 over cosine y. And that's really just what? Secant y. Now, as nice as that looks, it's not our answer, because our original problem, right, y equals arc sine of x, wouldn't we expect our derivative to be in terms of x and not in terms of y? Right? Like if I write down y equals x squared plus 2x and I ask you for the derivative, you're going to say 2x plus 2, right? 2x plus 2. 2x. So x appears here, right? Here we're getting the derivative of y, and to do it, we need to know what y is instead of know what x is.
So you plug in what y is.
We can try and plug in what y is into here and get it in terms of x, right? But I'm going to show you something that's much more powerful and much more useful. than just trying to take y and replace it with what? Arc sine x? In my opinion, this is more useful. Let's see. I mean, if you take Cal 2 with me, you'll be saying thank you later. So once you're at this point, we are going to go over here to where we had a relationship between x and y that didn't have any inverse trig functions in it, right? It's just sine y equals x. It's a very clean equation, isn't it? It relates x and y together. What I'm going to do with that equation is I'm going to create what's called a reference triangle. You might remember this from pre-cal. Reference triangle. Now, do we all agree that I can draw a triangle? I mean, just arbitrarily, I can draw a right triangle right here. Nobody has any problems with that? Is that okay? That's my triangle? That I can label the angles and sides however I want, but it's a right triangle, so there's certain relationships that are true? Do you agree that if I label this angle y, and I label this side x and this side 1, that that triangle represents that equation? So let's see. Sine of y equals x over 1. That's what that's saying? Sine, on a right triangle, sine is which side over which side? Opposite over hypotenuse, right? So if I'm calling y my angle, then sine of this angle is the opposite over the hypotenuse. X over 1 is x. So that triangle gives me this equation is connected to this triangle now, right? And this is what I'm calling my reference triangle. I'm going to use this as a reference because what I'm interested in is what? What cosine of y is, or what secant of y is. Secant of y, same angle. So in order to figure out cosine or secant, you actually have to know which side of the triangle. The adjacent side, which we don't know, do we? But we have a formula because it's a right triangle, don't we? And so why don't we call this side A just for now? And we're going to figure out what A is. And I'm using Pythagorean identity now. A squared plus x squared must be 1 squared. So everyone familiar with a squared plus b squared equals c squared? Two shorter legs of a right triangle, square them, add them. That gives you the hypotenuse squared. So this means a squared plus x squared equals 1. Move the x squared to the other side. A squared equals 1 minus x squared. And finally, to get a, square root both sides. So a is equal to root 1 minus x squared. Now I technically should say plus or minus because I took the square root, except for the fact that a is the leg of a triangle, so it's not going to be negative. So is that okay just to take that one? So this side right here, a, is square root of 1 minus x squared. Questions? So back to this now. Once you've created your reference triangle, secant of y is the reciprocal of cosine. Cosine would be what? Cosine of y would be this over this, right? That would be cosine, adjacent over hypotenuse. But we want backwards. We want secant, so we want 1 over this, don't we? So the answer here is 1 over the square root of 1 minus x squared. Box it up. And then you can go check your formula sheets now.
Can we leave that later?
Huh?
Can we leave it?
Absolutely.
Back
Leave
on
it.
the bottom?
Leave it like that. Yep. Leave it like that. So in your formula sheets, they should have it. Yes?
I just have a question. Why don't you like pair if you rationalize it? Because I had to the other professor.
Oh, goodness gracious.
I just didn't know.
Okay, it's a skill that you should know how to do it. Okay, you should know how to multiply top and bottom by a square root to make the bottom no longer have a square root, right? Y'all been told that before, right? I wanted to avoid this, but I mean, it bothered me when I was a student too. So look, if you got this answer, right? Some instructors will tell you you cannot leave that answer like that, and that you have to come in here and multiply the top and bottom by square root 2 over root 2. That's what they tell you. And then they say, okay, you multiply across, it's root 2 over 2, root 2 is 2, right? So that's the correct way, and you have rationalized the response, right? Now, do you all understand that 1 over root 2 and root 2 over root 2, root 2 over 2, do you all understand that's the exact same number? Yes? So why in the world would they want you to write it this way? They tell you, well, you can't have roots in the bottom. Well, why not? I mean, it's the same answer, right? So why not? So here's why, all right? And I'm not defending that. I don't require this, okay? But let me explain why I don't require it. Back before calculators, all right, before there were calculators, certain numbers came up in mathematics a lot. Pi. So people before calculators and before Google, before Wolfram Alpha, had to just memorize these numbers, 3.1415. And depending on the level of your math dorkiness would, be how far you knew it out, right? And I know people that actually work here that are in their 60s that at one point in time had pi memorized out 120 digits and still know it at least 60. Okay, because they didn't have somewhere to go. Now, you could look it up online, you could get it out in millions and millions of digits. Who cares? But there were other numbers that came up a lot in mathematics, like E, which is approximately 2.718. And then there were some other ones, like root 2 would come up a lot, and that's approximately like 1.414. But you couldn't memorize all of them, right? But there were common ones, root 3, and you wouldn't need root 4 because root 4 is 2, right? But there were certain ones, so you would have to have these memorized. Understand? Now, if I have these memorized and I get an answer on a test and I have to do this computation right here, and I'm trying to get an approximate answer for that, I want you to now appreciate how difficult this would be. Right? I go back to old school division because I don't have a calculator. I put a 1 inside, and on the outside I put root 2. But I've memorized root 2 to be about 1.414. And now what I'd have to do is I'd have to ask myself, how many times does 1.414 go into 1? I'd say, it doesn't. So I'd put a decimal, I put a point, and I do that, right? And I'd say, well, how many times does 1.414 go into 10? How many? 8? 7? 8's too much. 7? So you might actually have to come out here on the side, 1.414, and multiply it times 8, and then start doing that, right? And that would be a pain in the ass, wouldn't it? Everyone agree? It would be 7. Then you'd have to continue through. You have to multiply this times this, and then carry it. Now, the other expression that's equivalent to that is this, root 2 over 2. We said that's the same number, right? Now, if you did this with division, look at it. 1.414 goes here, right? What goes on the outside? 2. Does 2 go into 1? No. Bring the decimal up. Does 2 go into 14? Yes. You see this? See how much easier that is to do? You keep going 707, and much, much cleaner to do that arithmetic by hand than it is to do it this way, which is the reason why you'd always want to rationalize your denominator. You're trying to make this number a nice number and this one ugly. They switch places. But other than that, there's not really a good reason. All right? So I remember when I first learned, I was like, man, that sucks. But you should always know how to do it because, if it's an algebraic expression, and someone says rationalize it, you're like, what? What does that mean? I mean, you should know that what they mean is multiply the top and bottom by the root, and then, you should know what the actual technique is. But as far as usefulness in terms of numbers, that's why if you look on your formula sheet for this derivative, which we just determined, right? The derivative of arc sine of x is 1 over the square root of 1 minus x squared. That's your derivative on your formula sheet. Notice they don't rationalize that. Because what's the point, What's the point of putting the root on top? It doesn't matter. I hope that answers your question.
I didn't know.
Yeah, it's kind of a crummy answer to your question because it kind of, I know for me, I was kind of upset about that. Because I was always told you have to. And I asked the question sometimes like, why? And the answer was just because you have to. And that wasn't, to me, wasn't a good enough answer. So, and then when I finally get the answer, I'm like, are you serious? That's why it's, come on. All right, well, that's the derivative of arc sine. Guess what's left? Derivative of arc cosine, derivative of arc tangent, derivative of inverse secant, inverse cosecant, inverse cotangent. So let's see if you can get the next one on your own. Or in groups, you can work together or whatever. I want to see if you can figure out if y is equal to cosine inverse of x. I want you to show that the derivative is, someone look it up on their formula sheets. Is that it? It's under your derivatives.
Next page.
They put the negative out front. I just put it up on top. Same thing. See, notice the negative in front of it? So I want you to actually go through what I just did. You know, do something to both sides. Go through, take your derivative, solve, and then do your reference triangle and put it all together. Yeah? Y'all talk to each other. I don't want to take too much time doing this. Bradley, you got anything going on there? No? Did you write down what I did on the other one? No?
Record it. Copy it off the recording.
Yeah. Okay.
It was a negative.
You got it? Okay. Yeah, so your triangle doesn't matter how you draw it, as long as it's a right triangle.
Right.
Okay. Y'all got a starting point here? No?
Somewhat.
Okay. So what did I do on the previous one? Took, not multiply, because sine's not a number or something, right? So you're taking sine on both sides, like a composition. Okay, yes. So in this one, do the opposite. Cosine. Yep, take cosine. Did y'all get this one launched off the ground yet?
This is just -1.
-1 over sine y? Okay, yeah, and then, yeah, all it's going to do is change it. So I'm asking you to show that the derivative is that. So you're just going to verify your answer. That's your answer. The one up. Not that one. Yeah. So if you get that, you're done, right? If you get this one in your board, you can try the arc tangent, which would be the next one. That one actually works out even nicer. Yeah, you got it. Negative sine of y. Negative, hold on. You got to start with this equation here. Start with that. Write that. Start this out to start. This is what you're trying to get to as an answer. Don't write this down. You have to start with this. You have to show that the derivative of this is going to turn out to be this. I think I'm only going to give you like another minute. Most of you should be close to being there on this. Yeah, sine y. Did you get it to work out?
I'm still working.
Okay, so your equation, what equation are you referring to create this? What are you using over here?
The cosine to put the values in, and I'm going to use sine, or use those values to find sine.
I see the problem. This should say right here, cosine of y equals x,
Equals x, okay.
right? Because you haven't taken the derivative yet.
Oh, okay.
Then x is next line, that's why it becomes a
Yeah,
1.
that's what it becomes
So this is the equation that you're going to use for that triangle.
Okay.
Cosine of y is x over 1.
It's kind of ties in the related rates.
What's that?
Kind of ties in related rates. When you select if it's.
Yeah. Show of hands, how many you got there? Okay, all right. Okay, so in a run through of it real quick, take the original equation, you take cosine on both sides, the right side just turns into x, left side is cosine y, you take the derivative with respect to x, derivative of cosine y is negative sine y times y prime, derivative of x is 1, solve this for y prime, divide through by negative sine y. And now you're trying to figure out what this is. So you go back to this equation. Before you took the derivative, that equation, you create your reference triangle. You say cosine of y equals x. Cosine, did y'all learn this thing, SOHCAHTOA? SOHCAHTOA? Anybody not ever seen SOHCAHTOA? Not ever seen? So everyone's seen that then? Okay, so cosine is adjacent over hypotenuse. So I need my adjacent side divided by my hypotenuse to be equal to x, so x over 1. And that allows me to get my other side, which I do my Pythagorean, and then solve for b, and then plug it in. Yeah. So sine becomes this over this. And then that means that 1 over sine becomes this over this. So, yeah.
And with the being negative cosecant, that's how you negative.
Yeah. And that negative can be down here, out front, or up top. It doesn't matter, negative sign. Any questions? Okay, now the next one I'm not going to derive, but I'm going to put up here because this is a very, very important one. The derivative of arctangent of x is 1 over 1 plus x squared, which is the same as 1 over x squared plus 1. Doesn't matter how you write the bottom out. This is one that should be put into the memory banks. The derivative of arc sine and arc cosine, those are ones that, yeah, they come up, and you should probably try and remember these formulas. But you have your reference sheet, and you can get to these derivatives. This one in Cal 2 will be used a lot, so it's just good to know the derivative of arctangent x, 1 over 1 plus x squared. Now there are 3 more, right? And I'm not going to go through their derivations. I'll just point you to your reference sheet. And it has them there, right? The derivative of cosecant inverse is negative 1 over x times the square root of x squared minus 1, and then there's 2 others, so there they are. So let's do an example that incorporates some of this. If y equals arc sine of the square root of x squared. Let's go 1 minus x squared. Find y prime. So what I've done so far, all right, so I've just reminded you that in pre-cal there were 6 trig functions. We already knew those derivatives. Then I reminded you in pre-cal there were 6 inverse trig functions, and I've just shown you how to derive the first one, made you do the second one yourself, and told you that there's 4 others. Now those are on our formula sheet. We can take off with that. We don't have to prove them each time. So if someone gives you a problem like this, we're going to use the formulas to find the derivative, but we have to employ whatever, chain rule, product rule, quotient rule, whatever's in the problem. So what do we have going on here? Chain rule, right? So we have to take derivative of arc sine of something. Inside of that is what? Square root. Inside of that, 1 minus x squared. So we have some chain rule going. So what is the derivative of arc sine of something? I'll remind you, because we just did it. The derivative of this, right? That's the derivative of arc sine of x. So in this case, the x is really the what? The whole root thing, right? So it's going to look like this. 1 over the square root of 1 minus, and then the square root of 1 minus x squared, right? This is the thing inside the sign. I'm going to take that, I'm going to square it. We agree? Times, now what? So now we're taking care of the square root part inside, right? The derivative of the square root of something is 1 over 2 times the square root of that something. The something here is what? 1 minus x squared. Are we done? No, continuing the chain rule times, we've done the square root, right? We did the sign a long time ago. Derivative, what's in there? Negative 2x. All right, let's clean this up a little bit. 2's cancel. Still have a negative here and an x. How about when you square the square root? Goes away. I'm just left with what? 1 minus x squared? But there's a negative in front of it, right? So what is going to be left under that square root? Just x squared? So 1 over the square root, I'll write it out slow, 1 minus 1 plus x squared times x, negative x, over square root of 1 minus x squared. When you square the root goes away, but then there's a negative sign which distributes to each one, right? Which makes this a minus, then a plus. Those ones cancel, and you get the square root of x squared. What's the square root of x squared? X. If x is positive, it's just x. So 1 over x times negative x over square root of 1 minus x squared. Cancel these x's out. So you get negative 1 over square root of 1 minus x squared. There. Does anybody have a question on that? Try another one. If y equals x natural log of arctan of x, find y prime.